Hello, everybody. My name is Samuel Martin, and I am a doctoral student in the Environmental Dynamics program at the University of Arkansas. My primary research interests are focused on the impact of overland flooding and channel dynamics on archaeological sites in vulnerable regions. My presentation today is a case study of such activity and the disproportionate risk posed by shifting hydraulic systems. I will be discussing a case study of a small unmanaged portion of an Ozark watershed to examine the possible exposure to floodplain activity that might occur due to changing alluvial systems as a result of climate change. This project that I am speaking about today has been of particular interest to me because the Ozarks are such a massive mosaic of different interacting hydrologic features. Additionally, there are a significant number of amazing archaeological sites that sit within the confines of inactive and active fluvial systems that cover a long temporal range throughout the state. By understanding the potential risk to sites, archaeologists can use this information to prioritize the excavation or preservation of the most vulnerable locations in the state. There is ample research on the coast of the United States demonstrating the impact that rising sea levels from climate change will have on historically significant sites. Currently, there is little data on how this will impact inland cultural heritage. This study will be a little different than the models done on coastal sites, which map out patterns of degradation as a component of inundation from rising sea level alone. Instead, I observe risk to archaeological sites as a combination of overland flooding and lateral channel migration. This process is simply the migration of a river's course over time because of bankside erosion and point bar deposition. Lateral channel migration can occur very suddenly when conditions allow. These events are known as river avulsions and can be incredibly damaging to the adjacent landscape. They occur in floodplains where deposition of bankside sediments has caused the river to become elevated relative to the area next to it. If this area should have a slope equal to or greater than the channel, it may become active during high flood stages. When rivers in Arkansas's Ozarks reach peak stream flow, they are often located within seemingly confined spaces because of high bankside slopes, wide channels, and incised natures. This does not mean that they are immune to the effects of channel activity. Depending on the watershed, there can be broad floodplains within individual valleys, such as along the Illinois River or portions of the Little Osage Creek. These areas are particularly prone to lateral channel activity, usually because the margin was developed by migratory events in the first place, giving it characteristics similar to the modern bed. Like the Arkansas River, significant waterways like the Illinois are highly managed and engineered to prevent overland flooding and the erosion of bankside sediments. The construction of levees, dams, and spillways helps to manage flood stage capacity and reduce channel velocity. Although, given the major floods in 2019 and levee failures along the Arkansas River, this is not always an exact science. In cases where failure occurs, this can have significant consequences for the people and landscape nearby. Satellite imagery along the Illinois reveals a significant amount of lateral channel activity, creating cutaways and paleochannels in the environment. The geomorphology and aggradation of the river makes it prone to the development of gravel and sandbars that are often inset into the swale topography. In areas with higher surrounding reaches, the river will destabilize the folded and faulted geology, causing problems for anything located nearby or under it. A sample of archaeological sites for this investigation was chosen along a Buffalo River tributary with characteristics similar to that of the Illinois. Each of these sites was located within a range of about 1 kilometer from the channel. This region was chosen because recent research suggests that it will be disproportionately impacted by increasing amounts of flooding when compared to the rest of the state over the next 30 years. Flood modeling was performed using the Army Corps of Engineers HEC-RAS utility. This stands for the Hydraulic Engineering Center's River Analysis System. It can use a variety of spatial data to create 1D or 2D models of a river's surface water profile. Data can be easily bounded within a high-quality digital elevation model, polylines, and knowledge about the local baseline hydrology. The scalar assumptions of flow are defined for you within the program itself. I used unsteady flow conditions in conjunction with monthly hydrograph data provided by the USGS. The 1-meter Arkansas DEM was processed in ArcMap before being exported into the HEC RAS interface. Unsteady flow conditions simply accounts for variance in depth and velocity depending on the time and location being recorded. This river had its largest peak stream flow ever recorded in last water year in 2019. The water year typically begins on October 1st and ends September 30th, but the USGS cuts off this particular watershed about a month before the end of last water year. Using these dates in lieu of a typical calendar year better accounts for the seasonal deposition of snow and the input of meltwater in the spring and summer. I used an estimate of Manning's N, assuming that it was a gravel-bedded river and that there was only some vegetation on the bank from farming operations or tree stands. Manning's N is a coefficient designed to scale the potential friction the channel and bankside landscape might impose on the river's velocity. I also used an estimate of the friction slope assessed from stream data with characteristics like that of the selected Ozark River system. The friction slope is an estimate of how the makeup and inclination of the slope affect the movement of water as it flows downwards. Flow in meters per second cubed was used instead of the stage hydrography data. It modeled a more naturalized system as the depths of the channel could often sink below that of the digital elevation model, suggesting the river was flowing underneath the gravel bed. It made it difficult, if not impossible, to capture with the necessary cross-section data in the model. The sample size had to be kept relatively small due to limitations with the program because it can be very difficult to account for small changes in the baseline data throughout very large watersheds. In total, I chose 8 historic sites and 8 prehistoric sites from the bank. Each group was split into 2 subsections based on their location relative to the severity of surrounding aggradation. By running the 1D model for 2019, historic and prehistoric sites were equally flooded, with 2 from each becoming inundated. All of them were in the areas of highest elevation and region of the most significant aggradation. The historic sites were only flooded during the peak high water periods in early March. The 2 prehistoric sites were flooded 3 times, once in early March, late April, and late May 2019. When the gradient of inundation is increased by a conservative estimate of 3%, no additional sites become flooded. This value was reported by the NASA Earth Exchange Global Daily Downscaled Climate Projection at RCP 4.5, the intermediate scenario of climate change. The 4 sites that were originally flooded do become significantly closer to portions of the channel experiencing increased turbidity and flow velocity with an average increase of about 4 meters per second. The stress posed by the increased velocity in these locations would make them likely candidates for future channel migration or avulsion events. Under these conditions, channel width has increased as well to infill and reactivate formerly unused channel scars. In the most extreme climate change scenario, with a daily increase of 9.5% in the volume of flow, again there is not an increase in overland flooding, but a significant increase in velocity, with an average increase of about 7 meters per second. Destruction of sites in these scenarios would not be driven by inundation, but by channel migration, encouraged by an increase in the erosive and depositional properties of the river system. Through this small hydrologic model, it was demonstrated that prehistoric and historic sites are equally impacted by flooding. As they were inundated during the highest recorded flood stage in the channel's history, it suggests that the impacts of climate change are already apparent in the landscape. Clearly, there are many factors that could affect this outcome, such as previous flooding or channel migration, washing away archaeological materials, and/or an incomplete survey of the area. It is impossible to know the details about a site that has been eradicated, but the significance of this project lies in assessing vulnerability as we attempt to model future changes in the landscape. Protecting sites from inundation can be a complex process based on the various parameters that increase the sensitivity of certain sites to flooding. Protecting them from lateral channel migration is an even trickier problem yet. Sites will need to be prioritized based on their immediate need, age, and site choice relative to predicted flood patterns. Investments into engineering projects would be worthwhile but costly endeavors that may have difficulty accounting for changes in the subsurface geomorphology and be at risk of future degradation when the maintenance costs outweigh the protective benefits. Additionally, as is the case for the watershed that I examined, there are environmental concerns that must be considered as it is located within the confines of the Buffalo River sphere of conservation. There are often situations where rather than preventing flooding, it will come down to how many floods that site might be able to survive. This could factor in the preservation and previous conservation work that has already been completed. In cases where the cultural resource may be facing complete destruction, I would propose it needs to be fully excavated, recorded, or entirely relocated. For instances of lateral channel migration, the likely answer lies in assessing the predictability of potential events. Examining areas of the greatest stress can help us elucidate these patterns so we can work to mitigate their impacts on the adjacent landscape. As this project develops further, there will be plenty of room to expand the sample size. The complexity of the flood model can be increased to include an indexing system that attempts to identify and prioritize sites with specifically programmed sets of characteristics. I believe that expanding this work will require a fieldwork component to observe possible vulnerability on the ground. This would also allow me to develop specific measurements of the Manning's N value and slope friction quotient for each location being studied. Additionally, there is plenty of free open source data that can be collated to observe the potential impacts of climate change in greater detail. I would like to thank Dr. Jessica Kowalski for providing me access to Arkansas archaeological site information. I'd also like to give a shout out to whoever developed the Mazda Graphic Interface 2.0. It works like a dream. If anyone has any questions about my process, I would be happy to talk about them in greater detail. Feel free to shoot me an email. Thank you very much for your time.